You appear to be muted. Is anyone else able to hear him, or is it just am I having issues on my end?
I don't hear him either, and I think he realizes that because he seems like he's doing something. So
Okay.
Let's see if this one works. Y'all hear me now?
Yes.
Looks like it's working now. Sorry about that, everyone. You hear me, Clarence? Good deal. All right.
I can hear you.
So anybody have any questions before we get started? We finished chapter 17 last time, in case you're wondering. Okay. Looks like the audio and video are now working okay. So I'm going to jump into chapter 18. Chapter 18 is on the kinetic theory, and I'm going to actually use it. And when we use that version of the ideal gas law that I showed you at the end of chapter 17, and we're going to come up with some pretty neat stuff. So what I'm going to do is I'm going to talk to you about that first. So what we're going to do is we're going to imagine atoms, molecules, whatever, a group of atoms or molecules or whatever. We're going to, you're a bit laggy too, crap. Okay, so my video's off. Is the sound lagging as well, or is it just the video? Because right now I don't need the video too terribly much.
The sound's mostly fine, but the video is very small.
Could you answer that? That would be great.
Yeah, it says your bandwidth is low.
Laggy as well.
No, the audio is fine.
Okay, well, I'll continue on. It's not so critical that you see me right now. Hopefully that'll clear up in a second. But in terms of audio, that seems to be working, so I'll go on. And in fact, let me for a second turn my video off. Maybe that'll speed the process up a little bit too. So what I'm trying to do in this chapter is we're going to take and imagine atoms or molecules, whichever you happen to have, and we're going to imagine them at the microscopic level, and that there's a 10 to the 36 or 10 to the 24th of them. So there's a buttload of them. We're going to just treat them like they're all in some sense identical, but it doesn't really matter too much. You could go back and change it where some are different than others. But the main thing is when they collide at the microscopic level, they're going to conserve energy. So it's going to be elastic collisions, whether they collide with other molecules in the walls of a container or with molecules inside the container. All collisions will basically be elastic. So we're going to assume that. In doing so, that means we have to assume that their duration of time where they're near other particles is very, very small, because otherwise the individual electric forces could act between them to speed them up coming towards them and slow them down and run away. We're going to ignore all that. So in doing that, that means we have to consider fairly decently high temperatures, not near 0 Kelvin, in other words, And we also need to consider basically that they don't have any intermolecular forces pulling them together. And it's not so much that we're doing that, we're just assuming that those forces are really, really, really small. And when we make these assumptions, and your book has them listed in the beginning of the chapter when we start to do it, when we make these assumptions, then we get what's technically called an ideal gas. And in fact, you can do a lot with an ideal gas. For instance, we can model the interior of the sun. We can model the early universe right after the Big Bang. We can model that all in a ideal gas type scenario, because, you know, at high energies, those little forces between them are irrelevant. So that's what I'm going to do. I'm going to turn the video back on now. Hopefully. I cannot hear y'all. That is definitely the case. I cannot hear you, Jasmine. So you must have been answering me. Why am I not hearing you though? That's weird. Let me try now. Can someone please speak to me? Anybody say anything?
Can you hear us? Can you hear us? No? Can you not hear me?
Can you hear me?
Nothing there.
Testing, 1, 2,
Yep,
3.
I don't hear you guys at all. Y'all have to, I guess you'll have to type if you have any questions. Good Lord, this is a crap show. Clarence, can you unmute and let me see if I can hear your voice? Just because you're the face that happened to pop up at the top.
Can you hear me?
I've got nothing.
Are you hearing any of this? Nothing? Yeah.
Everything looks okay on this side. Let me check something real quick. Oh, looking for my glasses. Can't find my glasses. They're not on my head. Ooh, that was rough. I have a mute button. I wonder if I accidentally hit that. Nothing that appears to happen when I say, oh, there it is. Okay. So I seem to have the volume up. That's a good thing. I got it to 100% now, but I'm still not hearing anybody saying anything. So Aiden says he can hear everyone else talking. And Aiden, can you hear me talking as well? Okay. Well, I guess we'll just go on, and I will try to keep an eye on the chat so that I can make sure you guys, if you have a question, I can answer it. So sorry about all this kerfuffle. Hopefully it'll straighten itself up in a few minutes, but I'm not overly confident of that. So anyways, let's go ahead and turn on our document cam so you can see. Just had another student come in. I'm going to turn on our document cam so you can actually see what I'm talking about. So we can imagine, for instance, a box. Let's say we have a box like this, and let me again turn the camera on. So we have a box like this. And what we'll say is this side has an area A, as does this side. And in fact, this length right here is L. Okay, now let's get it sharpened up a little bit. Better than that, better than that. Put my pen over there, see if I can do better. Whoa, Nelly. There you go. Okay. And what we're going to imagine is these molecules are like little billiard balls. And at one particular point in time, for instance, this billiard ball might be traveling in that direction. I'm going to assume this is, say, the positive X direction. Let's say this is the Y direction. And let's say this is the Z direction, okay, a right-handed coordinate system. So what I'm thinking about is over an interval of time, this ball might actually come this way and bounce against the wall, as is well the case with this ball going this way. Now it has a component, obviously, in the X direction, the Y direction, and the Z direction, but all I'm considering right now is the component in the X direction, V sub X, okay? So it obviously, like I said, has a Z component, which maybe is this way, and a Y component, which is maybe that way. So you can see all the different components. Now, when you do this, you might want to think, well, what actually causes the pressure? If this is what atoms and molecules are doing, we suspect because of temperature, they're actually kerfuffle. If all the atoms and molecules are moving, and we suspect they are as a result of just having a temperature greater than 0 Kelvin, then they're going to collide with the walls and they're going to collide with each other. So what we're going on is we're going to say that a certain number of molecules is going to hit this wall, and that'll add up to give you a whole pressure. And in fact, the average amount will be so large that it's always going to maintain that pressure. So when we go to do that pressure, what we say is pressure is equal to the force divided by the area. That's the definition of pressure, the force divided by the area on which it acts. Now, the force, according to Newton's second law, is delta P over delta T. So what we're going to imagine is this is the left wall. And we're going to see this particle of mass M is coming this way. Obviously, the only component of it that matters to us is this V sub x one, but it's going to come this way and then bounce off like that and leave with a velocity V as well. Now, since kinetic energy is conserved, and of course, momentum's always conserved, what you end up getting here, or I say momentum's always conserved, assuming the net force is 0. But in this case, you'd have to include the wall as part of the net force or the net system, because otherwise the momentum sort of disappears. But what you get here is that the particle has an initial momentum, P initial, is equal to negative, and this is the X component, negative M V sub X. So that's the X component heading to the left to hit this wall over here. Again, I'm pointing to that back wall, that left one, this wall right here. Okay. And then after the collision, if kinetic energy is conserved, then that means 1/2 mvx squared is going to have to equal 1/2 mvx final squared. And the only way that happens is if Vx and Vx final are the same. So that means the final momentum in the X direction is positive mvx. So that delta P is equal to mvx minus negative mvx, which is equal to 2 mvx. Does that make sense to everyone? So we now say this is 2 mv sub x over delta t. Now we need to figure out, well, how many times is this going to happen in a time interval delta t? Well, you can say that delta t is actually, you can treat delta t as like it's a certain interval of time and figure out how long does it take before this particle say hits that wall and comes back and hits it again. Well, in that case, the delta t is twice of L, and then that's divided by that V sub x. So just that one particular particle is going to be doing this. Now, in the intervening period, it could actually bounce off of other things, but it's going to still not change the x velocity significantly. When it connects on the walls, it's just going to bounce back and forth, and it's going up and down. But we're not paying attention right now to any collisions with the top wall, the front wall, the back wall, the right wall, or the bottom wall, right? But that motion is going on too. So the net effect is, since it's elastic collisions, is this thing has a x component of velocity that goes bang, 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 even though it's also moving up and down. So now we can put all this together and we'd say pressure is equal to 2 mvx over delta t over A, and that's going to be 2 mvx. Delta t is 2L over Vx. So now I got a Vx squared up there. And then all that's going to be divided by the area. So if I manipulate this a little bit, I can say the 2's cancel out. I get mvx squared over a times L in the bottom. What's a times L? Anybody recognize what that would be based on this figure? You might need to type it. I still can't hear you guys. Use your knowledge of the calculus. What does the calculus tell you? Yes, Aiden said it. Yes, that is the volume. So now what we have is P is equal to mvx squared over V. Wow, that's amazing, right? The pressure times the volume is equal to mvx squared. So the pressure times the volume is actually equal to mvx squared. Now, the problem is that's just Vx. And in fact, the total volume, or excuse me, the total velocity, V squared, should be given by Vx squared plus Vy squared plus Vz squared. And there's something called the equipotential theorem. That basically says, hey, in random sets of things, every way something can have an energy, an equal amount of that energy is going into that way. So basically, if the energy is 1/2 mv squared, well, there's 3 tranches, if you will, of categories for the V, and that's the Vx, Vy, and Vz. And what that says is each of these will get 1/3 of the energy. So that means Vx should equal Vy should equal Vz. So Vx equals Vy equals Vz implies that V squared should be 3, or excuse me, yeah, V3, V squared should be 3Vx squared. In other words, this would be Vx squared plus Vx squared plus Vx squared, so that's 3Vx. So that actually allows us to relate Vx squared to V squared. So now I can say, well, PV is equal to 1/3 mvx squared. Now, if I go ahead and assume that we're going to have to take the volume of all this stuff, okay, or excuse me, take an average of all this stuff, this is just the momentum as a result of one particle. This is just the pressure times volume as a result of that one particle. So what I want to do is take this figure and take an average of all that. So what I want is V squared average, which is called the root mean square. So we're basically going to take the square, the average of the squares, and that would of course be Vx1, or let's just call it V1 squared, make it a little more sensible. V1 squared plus V2, actually leave that off, plus V2 squared plus V3 squared plus ... on up to plus Vn squared, where n is the number of particles. So if I took all those and then divided them by n, then I would get V bar squared average. Okay. So that means I need to take this and multiply it by n. Now I have over 3 mv bar squared. Okay, so now I have P times V is equal to all that. And before, we actually learned that PV is equal to N times the Boltzmann constant times T. So what we have now is that N, combining these two, NKT is equal to N over 3 times MV bar squared. So the N's cancel out. And in fact, if we want to make this potential energy, or excuse me, into kinetic energy, I'll multiply both sides by 3/2, or excuse me. Yeah, I'll multiply both sides by 3/2, and I'll say 3/2 KT is equal to 1/2 mv bar squared. That's the big result. That's the super important big result. And this is for just, you know, single molecules, single atoms, not ones that have any structure, like could rotate and or stuff like that. So we're treating them as individual billiard balls. It turns out this 3 is the number of degrees of freedom, because we could move in the X direction, Y direction, and Z direction. And in fact, later on, we'll learn that when you actually distribute energy amongst a bunch of atoms or molecules, that equipotential plays the same role again. And in fact, you might actually get not only 3 tranches for Vx, Vy, and Vz, you might also get 3 more for moment of inertia, omega squared about the x-axis, omega squared about the y-axis, and omega squared about the z-axis. In other words, the kinetic energy is going to go into those 6 tranches as well. And you could even get another one where the molecules are oscillating back and forth. So you can get like 7 or even 9 different degrees of freedom. Right now, what we found is the degrees of freedom is 3 for a basically a monatomic type gas. So what we have here is that the average kinetic energy of the molecules is equal to 3/2 kT. And that is our modern definition of temperature. Okay, when we're talking about temperature, say the human body having an average temperature of 98.6, which very few people actually nail it at 98.6. But the point is, if you average them all up, it would, of all the people in the world, you'd find that on average, it should be very close to 98.6 degrees Fahrenheit. What this is saying right here is that you can get a value equivalent to 98.6 degrees Fahrenheit by doing this. You can go in and survey every individual molecule or atom in your body and say, hey, and we're stopping time while we're doing this, mind you. So stop time for however long we need, and then we run in and we start surveying every molecule and atom that's in our body. And we write down quickly, what's his mass, what's his average velocity, what's his mass, what's his average velocity, what's his mass, what's his average velocity, what's his mass, what's his average velocity. And what we do is we take those average squares of velocities and we multiply each of those by their actual masses, and then multiply each of those by 1/2, add them all up, and divide it by the number of particles. Then I have the average kinetic energy, right, using kilograms and meters per second for velocity. And then if I multiply that by 2/3 and divide it by the Boltzmann constant, the 1.3807 times 10 to the -23rd, this figure right here, if I do that, then I'll have the temperature in Kelvin, and all I got to do is convert it to Fahrenheit, and lo and behold, we get 98.6. So that's what this equation says. That's a really big deal. And in fact, we'll later pursue the idea of internal energy of a gas or of a solid or anything like that. And it turns out that that internal energy really is the sum of the different varieties of kinetic energies that the molecules or atoms can have. And since we know this, and it fits, by the way, it fits experimental data really well. Since we know this, we can then determine, of course, the total internal energy. And that's going to allow us to have an internal energy function that we can use in the next chapter. So now that you've seen where this came from, and hopefully could regurgitate it on your own, because that's sort of the purpose of this, is to teach you enough kinetic theory where you could go on and do stuff on your own. So what I'm going to do right now is I am going to work a common example. So let's work out example 1. Oh God, I need my glasses. So example 1. What are the VRMS? Remember what I said, when you take the sum of the squares of the velocity and then divide that by the number of particles, you get the root mean, and then, well, then you got to take the square root, you get the root mean square, and that's what this is equal to. So you can also say this is equal to 1/2 m v bar squared, like that. So what are the root mean square velocities of O2 and N2 at room temperature? At A, room temperature, and B, at 0 degrees Celsius. In other words, the freezing point of water. So we're going to do that. All we have to do is figure out what those masses are and that sort of thing. So we know the average kinetic energy is just given by 3/2 kT. So we can do that immediately. But far as the M goes, we got to look that up from our periodic table of elements. So part A, we'll say 3/2 kT, which is your average kinetic energy, is equal to 3/2 times 1.3807 times 10 to the negative 23rd. Just want to double check. Joules per Kelvin times, now 20 degrees Celsius, of course, is 293.15 Kelvin. So let's do that calculation real quick. And this will be something that we can use repeatedly, of course. So 1.5 is the same as 3/2 times 1.3807 e to the negative 23 times 293.15. So you can see that's what I did there. Equals 6.071 times 10 to the negative 21st. 6.071 times 10 to the negative 21st joules is the answer. Notice the kelvins cancel out with the kelvins in the bottom, and you get the joules. Whoa, I'd slipped my whole page down there. Sorry about that. So that's the kinetic energy average. Now I've got to break it up into nitrogen and oxygen. So what I know is the average kinetic energy is 1/2 m v bar squared, right? That's equal to the 3/2 kT, which I'll keep it in that whole form because I've already calculated that for us. But now what I can do is I can multiply both sides by 2 and then divide by m. So I'll say 2/m times 3/2 kT is equal to v squared. And then, of course, that means v is equal to the square root of 2/m times 3/2 kT. And again, I'm just keeping that because I did that. You obviously, the formula you would want to use, if we hadn't already calculated that like we do, in algebra-based physics, you'd end up getting this 2 canceling out with this 2, and this 3 would be over top of the m, and you get square root of 3 kT over m. So that's a formula that you can use repeatedly. But I'm going to say v is equal to the square root of 2 divided by, now the mass of O2 is equal to, you can look it up, it's basically 32 because it's 16 for oxygen, it's 14 for nitrogen. And when you multiply that by 2, that gives you 32. And then times the unified or atomic mass unit, which is 1.66. Remember that 1 over Avogadro's number that I taught you? That's 1.66 times 10 to the negative 27 kilograms. So now all I have to do is put that figure, which is, let's see, 32 times 1.66 e to the negative 27. That's 53.12 times 10 to the negative 27 times what we got before, which is 6.071 times 10 to the negative 21. And that was joules. and this was kilograms. And now all we have to do is do that and take the square root. So I'm going to say this figure 2 divided by it. And then I'm going to say times 6.07. Actually, I don't have to write that out. I can use my trusty calculator to pull it down from above. And then I'll take the square root of all that. And I get 478.1. And really, we're actually only using what, 2 sig figs. So I really should round it here. And if you notice, a joule is a Newton meter. So, and a Newton, of course, is a kilogram meter per second squared. So a Newton meter is a kilogram meter squared per second squared. And then I'm dividing out the kilogram here. So I end up getting meter squared per second squared. Take the square root of that. That gives me meters per second. So, you know, that's on the order of 1,000 kilometers per hour. So that's pretty darn fast. And this is for O2. The other part we wanted to know for nitrogen, and I think you can tell the difference would be instead of having 32 in the bottom, we'd have 28. So we did get, this was 53.12 times 10 negative 27 kilograms. So what I'm going to do is I'm going to say, okay, well, the velocity of O2 is equal to, or excuse me, into the velocity of nitrogen, of course, is equal to the velocity of O2 times, now I can just take the 32 that I had in the bottom and cancel that out and replace it with a 28. So that's all I have to do to change this to the nitrogen case, is I just have to multiply this number times the square root of 32 over 28. That's just the easiest way to do it. You can go back and do all the calculation you want any way you want to, but I'm just doing what I think is the easiest way. So I'll multiply that by the square root of 32 divided by 28, because again, M nitrogen is equal to 28 times blah, blah, blah. Okay. So when I do that, you can see I just took the answer that we had before, the 478, and I multiplied it by the square root of 32 over 28. I hit enter and I get 511.11. Meters per second. Again, I'm really only used 2 sig figs, so these are 3 extras on this one. But now you see the velocity of the O2 at 20 degrees Celsius, and the velocity of N2 at 20 degrees Celsius. Now, if you wanted to correct these for 0 degrees Celsius, I think you can see, oh, it's just the difference of the square root of the difference in temperatures. So I can take velocity of O2 at 0 Celsius is just the velocity of O2 at 20. And this time I'm wanting to replace the temperature of 293.15. So I'm going to cancel that out and multiply it by the new temperature, which would be 273.15, because it goes on the top, and then take the square root of all that. So in other words, I just have to multiply that velocity times that factor. So I'm going to take the 478 that I got. I'm going to say enter. I'm going to multiply that by the square root of 273.15 divided by 293.15, and I get 461.51. Meters per second, and that's O2 at 0 degrees Celsius. So it did slow down significantly. Went from 478 to 461, and now I can do the same thing for V into at 0 degrees Celsius, it's just going to be V into at 20 times the square root of 273.15 over 293.15. Again, I'm just doing the quickest way, but y'all should, do whatever you want. Use this original formula if you want to. Just do 3 kT over m each time, doesn't matter. But I'm going to take that 511 now, and notice I'm going to hit enter, and I'm going to multiply that by, and here again, I can use my smart calculator. I can hit enter on that, and check it out. I'm going to just scroll over here and erase the velocity part. And now I've automatically got what I want. And that's 493.38. Again, only 2 sig figs are relevant here, so I'll do that. And I'm going to box this one off in black. So the physics that you should learn here is, one, hey, I can now calculate speeds of molecules and atoms. And in fact, you can even do the same thing with electrons, as I'll do in a second. But in there, you just use the mass of the electron instead of the mass of a particular element. Kendrick just evidently came in, so I'd let him in. All right, so you see now that the O2, which by the way is more massive, this is part of the physics as well. The kinetic energy is distributed equally under each molecule. So the kinetic energy is really what matters. Well, a molecule that has that's made of O2, O2 molecule is heavier than an N2 molecule, so it's actually going to go slower than an N2 molecule. So that's why you're seeing 478 for the O2 versus 511 for the N2. Similarly, when we got to 0 degrees Celsius, we went 461 for the O2 and 493 for the N2. So that's something very important. And that comes up, for instance, in the study of astronomy, particularly planetary astronomy. As you know, all planets, as we learned in the gravity chapter in back in 241, all planets have a certain escape velocity. If the gravity is actually what holds the atmospheric gases to the actual planet, it turns out that whenever the average, or excuse me, whenever the temperature is such that the average velocity of a molecule is about 1/6 the escape velocity, then that molecule will leave. So you can see things like, well, the heavier molecules are more likely to stick around because they're going to be going slower, whereas the light molecules like hydrogen and helium are likely to disappear. So that's one of the fundamental ideas that you use in astronomy and astrophysics in general. Not only that, you can also think about, well, if you want something to go really fast and you have a certain amount of energy, for instance, like the 1 tera electron volt particle accelerator, if you want the thing to go as fast as possible, then you choose the mass that's the smallest as possible. So that's another issue as well. All right. Any questions on that one? All right. I forgot to write something really, really crucial. And that was 11/18/21 PHY 242 D01B. All right, so no questions on that. Pretty straightforward, right? Everybody understands? But that is a cool new tool that you have. And in fact, I'm going to give you another problem. So here's example 2. The core of a star must reach about T equals 10 million Kelvin for hydrogen to fuse into helium. And I guess I'm on a random capitalization spree. Evidently, an element became something I had to capitalize out of a great deal of respect for, I guess, to fuse into helium. How fast is a proton traveling at that temperature. And what is its kinetic energy? Now, this is a little sketchy because at 10 million Kelvin, we actually might be forcing a proton to be going at relativistic speed. So we would have to use a different version of kinetic energy. But let's ignore that for just a second and hope for the best. Let's hope that it's not. Okay. So what I know is that the mass of the proton is equal to 1.67 times 10 to the negative 27th kilograms. And now I'm going to verify that because I don't trust myself in my old age anymore. So the proton rest mass 1.67 10 to the negative 27th. That works wonderfully. Okay. And we know the temperature is going to be T equals 10 to the 7th Kelvin. So what I'm going to do is I say, well, 1/2 mv bar squared is equal to 3/2 kT. So I can calculate, cancel out the 1/2 on both sides, and I'll get V is equal to the square root of 3 kT over m, just like we found before. So obviously this is going to be something we'll use a lot. So it'll be the square root of 3 times 1.3807 times 10 to the negative 23rd joules per Kelvin times 10 to the 7th Kelvin. Now be careful with putting that in. What you don't want to put you don't want to put 10 times 10 to the 7th or 10 when you're doing scientific notation. You just want to write 1 times 10 to the 7th. Okay, just be careful with that. That's a mistake students often make. So there's my 3 kT. And now I'm going to divide that by 1.67 times 10 to the negative 27th kilograms. And that'll give me the actual velocity. When I do that, I get square root, square root of 3 times 1.3807 e to the negative 23 times 1. Listen how I'm saying this. I'm doing 1 e to the 7th. That's how I put in 10 to the 7th, just so you know. 1 e to the 7th. And I only have one thing in the denominator, so I don't need to use a division, a parenthesis. I just used division and made sure I didn't pop outside of my square root. I'm going to do 1.67 e to the negative 27. And that gives me 498.0 times 10 to the 3rd meters per second. So that's roughly, well, that would be what, 4.98 times 10 to the 5th. So yeah, that's not an appreciable fraction of the speed of light. So I say that's just fine. So the velocity of the proton at 10 to the 7th Kelvin is about 498,000 or 498 kilometers per second. Okay, so that's pretty darn fast. Now, the other thing I asked you about is what's the kinetic energy. So let's just calculate that, and that you don't even need the mass for. You just say kinetic energy average is just 3/2 kT. So that's 3 over 2 times 1.3807 times 10 to the negative 23rd joules per Kelvin times 10 to the 7 Kelvin, and we get 1.5 times 1.3807 e to the negative 23 times 1 e to the 7, and I get 207.1 times 10 to the negative 18th joules, but I'm going to convert that to electron volts. So I'm going to divide that by 1.602 e to the negative 19. Hopefully y'all remember that. Uh-oh, just did something weird on my calculator. What happened? Okay, so that's 293 times 10 to the third. Whoa. Times 10 to the third electron volts. Or that's 1.293 kilo electron volts. Okay, so that's really what the kinetic energy of the protons are at 10 to the 7th Kelvin. So I'm going to circle that and tell you why I asked it at all. So what our argument was that the core of a star needs to be about 10 million Kelvin before it can fuse hydrogen and helium. To fuse hydrogen and helium, basically hydrogen is at 10 million Kelvin. It's very rare that you'll find the electrons still attached to the protons. So it's basically just a proton. The hydrogen atom is just a proton at that point. That's what makes the sun a plasma, because the electrons are freely moving around, as well as the neutrons and the protons, all that are moving around somewhat separately, but the neutrons usually will bind up with other nuclear particles. So if you think about it, you have to have enough speed to overcome the Coulomb barrier, which is to approach the nucleus of the hydrogen atom, or in other words, the proton. So if you actually calculate the potential energy of the hydrogen atom, what you'll know is the potential energy is actually equal to the volts per Coulomb. So, or excuse me, the volts times the Coulomb, and the voltage, of course, is just 1/4 pi epsilon naught times Q over R. So now what we're going to do is Q squared over R to get the actual energy. And when I do that, we can do the charge of the protons is 1.602 times 10 to the negative 19th coulombs. That's going to be squared over 4 times pi times 8.85 times 10 to the negative 12th. And that's supposed to be in units of newtons meters squared per coulomb squared. There's other ways you can write it, of course, too. And then all that times basically what we want is it to be roughly around 10 to the negative 14th. So 1 times 10 to the negative 14th meters. That would mean the two things are really very close to each other. So let's calculate roughly what that is and see if we're in the same ballpark with the energy. So I'll say 1.602 e to the negative 19 squared. I'm going to divide that by parentheses 4 times pi times 8.85 e to the negative 12 times 1 e to the negative 14. So that gives me 23.08 times 10 to the negative 15 joules, which I convert to electron volts by dividing by 1.602 e to the negative 19. And that gives me about 144 times 10 to the third EV, or 144 kilo electron volts. So we suggested it was going to be about 1.293 kilo electron volts, but I found that this basically bringing a proton next to another proton, it requires about 144 kilo electron volts. What we're missing here, the difference is that the strong nuclear force happens to be a factor of maybe or several factors of 10 more powerful than the Coulomb force. So once you get into a close enough range, and this is actually really well close enough, then there's actually going to be a force of attraction that sucks them together, even though, like I said, they're both positive particles. So the Coulomb repulsion would be strong, but the strong nuclear force, which is very short range, it can't reach out very far. But once you get to this type of range, then that strong force will kick in and pull them together. So this was what seemed like a lot less kinetic energy than necessary, but that just gives you an idea about how strong the strong nuclear force is. Basically, you can say if I multiplied this by 100, I would almost be strong enough. So in this case, the strong nuclear force is more than a factor of 100 stronger than the Coulomb force. So that's a whole neat problem all the way around. Any questions on that one? Let me check my units on this. This is Coulomb squared. That cancels out with Coulomb squared. Nope, that Coulomb Newton. Oh, I had this upside down. Good. This is not. Remember, epsilon 0 goes in the bottom on Coulomb's law. So my units were actually quite jacked up. The units for 8.85 times 10 to the negative 12 actually has to have the newtons in the bottom and the Coulomb squared on the top and the meters squared on the bottom. Yeah, that makes sense. So let's check the units. Now we can see that we're going to have basically Coulomb squared is going to cancel out with Coulomb squared. I get a meter squared up top and a Newton up top, but the meter squared is going to cancel out one of the meters. So that does give me joules. So that all works out. Okay. Any questions on that? All right. So that's what I wanted to show you with regards to the 3/2 KT and all that sort of stuff. We've now calculated, actually your book did the same thing. That's your book did the same thing for the speed of the air molecules at 20 degrees Celsius. My example actually included the 0 degrees Celsius. So that's the only difference. Let's check what my answers look like versus theirs, just in case I made any arithmetic errors. They found the root mean square velocity for the oxygen to be 480, which they said is 1,700 kilometers per hour or 1,000 miles per hour. And that's clearly much greater than the speed of sound, which is 340. But they found the root mean square for nitrogen to be 510. We found 511. So that was good. So yeah, our figures do actually match up quite well. Now, the next thing we need to talk about is something called the distribution of molecular speeds. And we call it the Maxwell distribution. So one thing I want to point out to you before I do that is that this root mean square velocity that we're calculating, that's not really the same thing as average velocity. In fact, there's a bunch of different ways to do to figure out what velocity an atom or molecule might actually have. So root mean square velocity literally means take VRMS, which is what we've been calling V ball squared, something like that. That's actually the square root of that. And it's equal to V1 squared plus V2 squared plus ... plus Vn squared divided by n, and then you take the square root. Okay, so let's consider some velocities. Let's say V1 is equal to 1. Let's say V2 is, and this is meters per second for all of them, but I'm only going to write it for the first one, is 2. V3 is 3, V4 is 4, and V5 is 5, and V6 is 6. Okay, so let's take those. The average velocity of all that, V bar, would be 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by 6. And when we do that, we say 1 plus 2 plus 3 plus 4 plus 5 plus 6. And then we divide that by 6 and we get 3.5 meters per second. Now let's do V root mean square, just so you can compare what these figures are. In fact, we'll give you a result that tells you more accurately how to relate the three. There's going to be 3 different ways about how to relate those 3 different ways of calculating an average velocity in some sense. So in this one, it's going to be 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared divided by 6. And then we take the square root of all that. So when I do that, I'll say 1 squared plus 2 squared plus 3 squared plus 4 squared. I don't know why I'm making it into a song. Plus 5 squared plus 6 squared. So you can see I wrote all that stuff out and say equals, and I'm going to divide it by 6. And now I'm going to take the square root of that 15.1667. So I'll say square root, answer, and boom, I get 3.89 meters per second. And it's 3.894444, but that's plenty enough, right? Because I only gave you 1 sig fig to begin with. So you can see that those 2 velocities are different, and you shouldn't expect them to be. Now, you should expect them to be. Now, the other thing is, how are velocities distributed amongst molecules and stuff like that? Well, that's the Maxwell-Boltzmann distribution that Maxwell, James Clerk Maxwell, the same guy that we talked about for the whole first half of the semester when we were doing Maxwell's equations, he also derived this distribution. We're not going to derive it here. They usually do that like in a modern physics course, but it's really pretty cool. And the function is, and what this is actually the probability that a particle will, or that a atom or molecule will have a velocity between v and v plus dv. Okay, but in order to actually get the number, you'd have to multiply it by dv. So I'm just going to give you this part now. It's 4 times pi times the number of particles times m over 2 pi kt. That whole quantity is going to be raised to the 3/2 power, and then times v squared, and then times e. Yeah, it's nasty, ain't it? This is definitely one you want to write on your equation sheet. Times e to the negative 1/2. Now it's going to be mv squared over kt. So that's the Maxwell-Boltzmann distribution. Okay. And if you did a plot, say, of f of v versus v, where f of v is the number of molecules, okay, again, the number of molecules that have placed between v and v plus dv, you get a sort of steep line on this side, and then you get a peak, and then a gradual decline. So this side should be basically way more junk on this half than there is on this half. Very, very low here, and quite a bit elongation on this side. Okay. So with that in mind, it turns out there's 3 types of velocity. If you take this one, since this is a probability distribution and it has a maxima right there, that's actually the most probable. So that's v sub p, which is most probable velocity. So that's the most probable velocity that a molecule will actually have. And then right next to that, you'll see v bar. And then right next to that, slightly larger, you'll see VRMS. Okay, so that's how you actually the different ways that you can actually talk about the velocities that molecules or atoms might have. So you got to remember that N is the total number in there, M is the mass of the particles, T is the temperature, V is the velocity, and of course M and K, they're the M again is the mass, but the K again is a constant, and the T is the temperature. So that's what that graph looks like. That's an important thing, and it helps us figure out stuff. So what I want to do first off, and your book does something like this too. Every book does essentially, but as soon as you get that distribution, the first thing you want to do is use it. So what we're going to do is we're going to use that to find out the most probable velocity. So here's example number 3. Let me check the time. Okay, looks like we're only going to have time to do this part. So example 3 is, what is the most probable velocity according to Maxwell-Boltzmann? Okay, so I've got the thing written here so we can see the actual distribution. But when you say most probable, what you mean is df of v with respect to v is equal to 0. That's how you find a maxima or a minima or an extrema of any type. Of course, the second test is, or the second thing you got to do is take a second derivative. And of course, if it's going to be a maximum, you need to make sure that that second derivative is negative. So let's do that first derivative. So I'm going to take d by dv of, now I'm going to get rid of a lot of junk, because the 4, the pi, the n, the m over the 2 pi k and t to the 3/2 power, those are all just constants. All I really have is a v squared and an e to the negative m v squared over 2 kt up there. That's the only part that really has a v in it. And I'm going to set that derivative equal to 0. So no matter what, these things are going to just disappear, because I'm taking the derivative of all this junk. This is just a multiplier. So now I end up getting d by dv of v squared e to the blah, blah, blah v squared. Okay, so I'm leaving off a bunch of junk right there. But the derivative of v squared is 2v, and then I have e to the negative mv squared over 2kt. Remember, using a product rule here. So now I've got to add to that the v squared. Now I'm going to take the integral, or excuse me, the derivative of e to the negative mv squared over 2kt. And that, of course, is negative m times 2 times v over 2 times k times t times e to the negative mv squared over 2kt. And then all this is going to be set equal to 0. So I get 2v times e to the blah, blah, blah. That e to the blah, blah, blah can't help us get to 0 at all. That's why I'm not giving that much shrift here. And then over here, I've got minus, notice these 2's cancel out. I got minus mv cubed, because it's v squared times v, kt over this, times e to the blah, blah, blah. All that's equal to 0. So I can say 2v minus mv cubed over kt is equal to 0. That allows me to say that 2v is equal to mv cubed over kt. And ultimately, I can pull this v over here by canceling it out. And now I've got 2kt over m square root is equal to v. So the most probable v, vp, is the square root of 2kt over m. we found the root mean square to be equal to the square root of 3 kt over m. Remember that? So the most probable one, as you can tell, is in fact a little smaller. It's 2 kt over m. Now, if you wanted to evaluate that second derivative, you can see what you'd have to do. You'd have to take the derivative of all this and the derivative of all that, and then you have to plug in that value, and I guarantee you it'll come out negative. So that's something you can do. I'm not going to, do it right now for you. Another thing you can do, though, is calculate the actual root mean square velocity if you wanted to, or you can calculate just the average velocity. And the average velocity is given by this. So just as a sidebar, I may or may not have enough time. What is V bar? Okay, well, an average, believe it or not, is just supposed to be an integral of what you're taking the average of, which is V in this case, times the probability distribution times dV. And of course, that will get you the sum of all the velocities, but then you got to divide that velocity by n to get the average. So what we have to do is actually take an integral of that god-awful, nasty-looking function, the Boltzmann function, okay, but with a v cubed instead of a v squared. So now I'm going to say, all right, it's going to be, oh, where'd I lose my Boltzmann? Oh, it's in the other page. Sorry about that. Bringing this back down. So what I'm going to do is I'm going to call out the 4 pi n and the m over 2 pi kt to the 3/2 powers. Actually, I forgot I was going to do that. That's why I didn't leave enough room. So I do 4 pi n times m over 2 pi kt to the 3/2 power. They're not going to play any role in this integral because they don't have any v's in them. So I now have the integral of v cubed e to the negative mv squared over 2 kt dv. Now that is not a fun integral. And in fact, you get to use integration by parts to do it, which most students I run into never really got a good understanding of it, but I highly recommend you figure it out, and maybe this is a good day to do it. So integration by parts is basically the integration of the product rule, and you end up getting the integral of u dv equals uv minus the integral of v du. And the trick to using it is there's always some part that's a bear to integrate, and then there's a part that's a bear to differentiate, sort of. But the main part, that the one of most concern, is the fact that you've got to integrate something that's really kind of hard to integrate. So in this case, this e to the whatever, that's a hard thing to integrate. So what you do is you differentiate that one. So in other words, you're going to call u from this thing right here, you're going to call u the e to the negative mv squared over 2 kt. So you say let u equal e to the negative e to the negative m over 2 kt v squared. Okay, then du is just negative 2 mv over 2 kt times e to the negative mv squared over 2 kt dv. Okay, so by doing that, I've now taken the thing that was going to be hard to integrate and just made it something where it had to be taken the derivative of, right? Now the other part is I'd say let dv equal v cubed dv. And of course, it's unfortunate that I used v here. Maybe I should call it a w. So let dw be that, okay? then that implies the integral of dw, which is actually w, is equal to the integral of v cubed dv, which equals 1/4 v to the 4th. So now that would say the integral of u dw is equal to u times w minus the integral of du. And you get u times, I know I'm about out of time here. I'd get u, which is negative 2 mv over 2 kt e to the negative mv squared over 2 kt. That's u times w, and w we found was 1/4 v to the 4th. By the way, these two 2's cancel out. And then minus the integral of, now I got to do du, which is the integral of negative, actually, I don't even have to do that negative anymore. I have the negative, but not the 2. So I got mv 2 kt e to the negative mv squared over 2 kt dv. So now it's a little easier because you can say let u equal mv squared over 2 kt. So I'll say let's do something other than u. Let x be equal to negative mv squared over 2 kt. Then dx would be equal to negative 2 mv over 2 kt times, actually dx would just be that times dv. So you can see you've already got a multiplier here, and now it's just taking the integral of e to the u. So you can do that now. We're out of time, but that's basically it. You can, the rest of it's just a little bit of algebra. Anybody that needs to go is free to. If you have any questions, please stick around. I'll probably try to finish this, but since time's up, I'm letting you guys go. If you have any questions, you'll have to type them though, or still not getting any sound. Clarence, can you see if I have any sound? Can you talk to me or something?
Can you hear me?
Yep, still nothing. Crap, boob, crap. All right. Well, sorry guys. Sorry for the discontinuity in the class today, but hopefully it'll work out next time, especially for lab, for instance. All right, you guys are free to go, and I will see you at lab and next week after that. We have class Tuesday, but not Thursday. Yes, that's correct. Does anybody know whether we got Wednesday off? I think we do. You have to type the answer though, because the stupid thing's not working.
I don't know why, but I don't remember why we're going off. What's happening?
Thanksgiving.
Thanksgiving. Ah, I thought that was yeah, I guess it is, yeah. Wow.
Nothing. Yeah, if you guys want some more time, we'll talk about it at the beginning of lab. If y'all want some more time, I can do that. But you'll answer questions first when you first get there, and maybe I can help y'all work it out. I had a question about the lab. I logged in late to the lecture period, which actually was the lecture period. I was trying to do the lab and was very confused, but I missed the lecture, but there was no video posted of the lecture for lab. Yes, I will go in and explain that again during our lab meeting. I might even be able to post the video on our class page instead of posting it on YouTube. Yes, there can be an extension for it. Anyone else? Okay. Yeah, it will be for the whole class. I'll give everybody some more time to do this lab. And for the lab, we only had to do a few specific parts, right? Yes, I think I'm on the same page with you, what you're thinking about, but yeah, you didn't have to do the, well, I mean, yeah, you had to do specific parts, but nothing from the lab manual necessarily. This was all a write-up of from the bottom of the lab write-up. It tells you exactly what's supposed to be in that lab, and you know, like a introduction and stuff like that. And those things are all supposed to be written, and each one turns into an individual one, and you do the analysis supposedly on your own. Anything else? All right, see you in lab. Looks like everybody's done. I'm going to keep working this integral out. I actually need an extra 2 here. So I'm going to have to make a 1/2 here. And I can do that by erasing this. And then this right here is now dx. So the integral of ex dx is just e dx. So I get negative mv to the 5th over 4 kt e to the negative mv squared over 2 kt minus 1/2 e to the negative mv squared over 2 kt. That should be it. Therefore, v, which equals the integral of v f of v dv over n, should be all that stuff that I took out before. 4 pi n times m over 2 pi kt to the 3/2 power times, if my integral is done correctly, which I'm questioning that right now, is mv to the 5th over 4 kt minus, I don't know how this 1/2 got there. Well, I know the 1/2 got there, but I don't know, something needs to be there to add up with this, and I'm not getting that. So anyways, I will refer you all to your book to see what happened. I might have actually made a boo-boo somewhere, but that's supposed to be what it is. And obviously all that has to be divided by n, so that gets rid of that. But anyways, I made some kind of mistake, and that's what I got. But I will try to work this out and post it as an independent video on my YouTube channel. Have a good one.